you're still holding office hours next week Monday, so the homework is due next week Wednesday. So these questions, first look on the discussion group. There's been a lot of kind of detailed questions. A lot of the answers are there already. So look there and ask the TA's questions about various some small details or post on the group. All right, and so then the following Monday, I think the data collection report is due. It's due pretty soon. Let's see, it's due on Monday the 24th, so that's the following Monday. So I'll talk more about this in detail next week on Wednesday. But the basic idea is I want you not only to find your data, but also to kind of try and start figuring out what sort of format that you want the data in, what sort of abstract representations you're going to do. So it's often not clear whether you have the right data or not yet until you realize, what the part of the data actually looks like that you can actually run an algorithm on. How much of it you actually have. So I want you to at least think about getting it into an abstract representation by then and write some short web of what we're doing. And I'll help to be able to guide you whether this data is a good match for your project or not based on this report. All right, so we're still talking today about
and you did some modifications. Did you change something in Newton?
so are there questions on something?
Euclidean.
Right.
That's what you call
so we're talking again about clustering, and we're going to be focusing
you have the solution. You have the solution.
Assignment-based clustering. And we very quickly at the end of class on Monday talked about the case. So again, the assignment-based clustering is where you're given a set of centers. And you can define this function P of C, which takes in the X. It's going to return the R min Ci in the set C from the distance from X to C. And so this usually means L2, but it can really be any distance, right? So any of the distances we talk about. And so we talked about very briefly the K-center formulation. So then the goal is just to find these centers and automatically clusters the data based on this assignment function. The K-center thing is when you're trying to minimize this set of centers to minimize the max X in some input data set of X minus the distance from X to its assignment. Right, so this looks, remember the input is going to be this is going to be the set of these points. And so then the centers may be elements of the set, but they might not be. And then based on these centers, you can define this function by essentially drawing this Bornheim diagram. And all the points which are closer to this point than any of the other points are in this cell. So these are in this cluster. Okay, so just by defining these center points, I've defined the cluster. So it's a compact way of doing it, and you can assign labels to all these if you want as well. So the K-center is to try and minimize the maximum distance. So that may be this furthest distance here from any of the centers to any of the points. So then the most famous one we're going to spend most of the time today on is the K-means formulation, which you want to minimize the set of centers, where you're looking at the sum over all of the points in your set of the distance from X to the assigned cluster, and you're looking at this square. And then kind of the third common one in the set that we will discuss very briefly, I call it the K-median. So it's called the versions, the other names for it, like K-medioid, I think is the same thing, where you're minimizing the C over the sum, and it's, instead of the sum of the squared distances, it's just the sum of these distances. So if you can't read this, it's the same as the K-means, but it does not have the squared here. Okay, and then this is the max. Okay, so I went through the Gonzalez algorithm for K-center very quickly on Monday, so I'm going to go over it again and say a few more comments about it. So it was this very, very simple algorithm. For K-center. Okay, and so all we need to do is define these K-centers, and K is going to be a parameter. So this is minimizing this set C such that the size of here is K. And so K is given as input. We can do techniques like this elbow technique or some other heuristics to come up with this value. Okay, so in the fall we're going to have the set CI, which is going to be a set of the centers we've already defined for I less than or equal to K. And so then the first, we start by defining the first center C1, and this is going to be, we can basically pick any point in our set, and we're going to do this arbitrarily. So arbitrarily pick a point in the set. This is going to be our first center. That could be, say, this one right here. We pick some random points. Do it at random. You can pick the first one in your data set and the ordering, anything you want. And so then you go through a fairly simple for loop. And you basically just have to do one thing. We do Cj is going to be the arg min of x in our set, or the arg max of all right, so what we do is we look at all the elements in the set, and we look at their distance to their assigned center, and we only use the centers that we've so far defined. We find the one that's the furthest away, and that's going to be our new center. And so we do this K-1 times, and that's it. And so then we can set that C is equal to, CK equals C1, C2, CK. Right, so this is the whole algorithm. Yeah.
What's this C sub I minus 1?
Yeah, so this is a capital C, and this is the set of centers we've defined so far, right? So we start by presetting it, so we pick any point arbitrarily to be the first center, and that means the first time through the loop, j is equal to 2. Sorry, this should be a j. Yeah. Okay. Sorry. Good. So then this is C, the set C1. So this is an uppercase C. Right, so if I took away these blue points, how's this going to work? I'm going to pick some point arbitrarily, and this one gets the label of C1. And now, when I go through, and this is the first step, then I'm going to go through this for loop. So let's go through for j equals 2. I find the point at x of all the black points, which is furthest away from its assigned center. Everything is assigned to this center because it's the only center I have. So that means I'm picking the furthest away point from here. And that's going to be this point. That becomes C2. Right? So now I have these Voronoi lines. So now, basically, I can draw this Voronoi edge line between these two, and all the points on this side are in this cluster, all the points on this side are in this cluster. If k was equal to 2, I stop. Right? If k is equal to 3, then I look at every point the distance to its assigned center, which is the closest one. So this to here, this point to here. So this is maybe the furthest away point. I could have, maybe this one is a little closer than this one is. So this point becomes C3. And now I have these new Voronoi line here. Right, so this line still divides these two regions, and this line divides these regions and these regions, okay? So now I've assigned all these points to this center and so forth. So that's the whole algorithm. All right, so okay, so this problem, as I mentioned, finding the optimal solution for this is NP hard. You basically can't do it. It's hard, NP hard to even get better than a 2 approximation to this quantity, the maximum distance. But this is guaranteed to give a 2 approximation. So if in the past I've given that as a bonus question, how to prove that. It's not too hard to do. So I haven't come up with the assignment yet for clustering. So the other things to note, so the other questions about this we didn't really discuss are, first, so how long does it take to run this out? Okay, so let's look. So this first part is not really doing anything, right? So I've got a for loop. Got a for loop here, and this is not really doing anything. All the computation is in this for loop, right? This for loop goes through k times. So we have a factor k for the number of clusters. And usually k is going to be much smaller than the number of your data points. So we'll look at it. So I go through this for loop k times. How long does this take to calculate? To find the point that's furthest away from its assigned center. But, well, in order to do that, I also need to know what is the right assigned center. So it turns out you can do this in basically n time, but you need to be clever because I don't know this assignment ahead of time. Okay, so I need to I actually need to do 2 things in here. So the first thing is I need to find the assignment function CI. Okay. The other thing is I need to find the R max x of. So I need to do 2 things. So once I have this assignment function, this takes linear time. I can check all the points. Right? So that's not. So this I can do in linear time. So this is times n. Can I find the assignment function in linear time? Can I do that in O of n time? Or do I need to spend... The naive way of doing it is, let's say that this value I is actually, or let's say it's j here. Let's say j is basically an order of k. It's at least k over 2 for half the round, right? So this is basically, so let's just say I have, this is looking at ck. So I need to find this assignment. How do I do this? I need to assign every point to one of the centers. Well, so if I don't have any more information, it's going to take, well, so the simple thing I can do is I can build one of these data structures we talked about a week ago on top of the existing centers, and then it's going to basically take n times only log k time, right? So I can build, so option 1, I can build a data structure on this set of centers ck, and then I can spend basically O of n times something like, if it works, if it's low enough dimensional space, it'll look something like O of n log k. In higher dimensions, or I need to use one of these advanced techniques, it may not really be log k. It may take longer. I use locality sensitive hashing. This is, I don't quite get a log k, right? But I don't actually need to do this. I can do something smarter. So option 2 is I'm going to use the assignment function c of k minus 1. Okay, so when I got to this step, at the previous for loop, I had the previous assignment function, which had, so remember when I was at this step here, before here, I had this whole thing, and I only had C1 and C2. And I knew this assignment function already, right? So what does that tell me about this point? If I knew this point was assigned to C2, then what's left for me to do to check, to build this assignment function, this new assignment function, where I updated only one center? What was that? Yeah, that's right. So I only need to check against the new center. I only need to check if this point is closer to C2 than it is to C2. Right? For this point, it was closer to C2 than C1. I only need to compare the old distance with the new distance. And the same, this point was closer to C1. I don't need to check against C2. Even though it's almost as close to C2, I only need to check against C1 because I know already that it's closer to C1 than it was to C2. So I only need to do kind of a linear number of comparisons to update from the old CK to the CK minus 1 to the new CK. So this can also be done in O of n time. So I have O of n time here and O of n time here. So and there's, if you want to work out in full detail, if you look in the notes, I actually wrote out some pseudocode with for loops, how to actually do this. So you can run this whole algorithm in O of n times k times, which is just it's pretty fast. Usually k is small, and n is the quantity you have to worry about. So this is a very fast algorithm. Okay. The one other thing I want to mention here, and this will be in contrast to in contrast to some properties with K-means we'll see, is that this works on any so this works where the distance is any metric, right? So that's where this distance here that I'm using in the assignment. If this is any metric, I can use this function, this same algorithm. Okay, so I'll still get this kind of 2 approximation to the optimal, this 2 approximation result. So any metric distance will work. I don't need to restrict myself to Euclidean distance. It doesn't need to be points in the plane. It's still going to be O of nk time to run it. Nothing I said was specific about the distance. So that's a very nice problem. It's very fast. It's very general, has pretty decent guarantees that work in practice. The downside is that it tends to pick points which are kind of on the boundary of your point sets, right? If you're looking at points that fix the furthest point away, these are going to kind of tend to be on the outside. Eventually, if you get enough centers, you may start to fill in some clusters in the middle, but it's going to tend to pick these outside points. So that's kind of the main disadvantage of this algorithm. Okay, so that's all I wanted to say about the Gonzalez algorithm. Now, let's talk about K means clustering. Okay, so so before this class, who had heard of K-means clustering before? And so who had used K-means clustering? So K-means clustering is actually the optimization thing you want to try and solve. It's not an algorithm. Typically, what you've used probably is what's called Lloyd's algorithm. So Lloyd's algorithm. So there's some document that he wrote in 1957, but it wasn't published until 1982. He wrote it down. He didn't think it was anything that important until it became very, very useful, and so eventually someone got him to publish it in 82. This is, one of the most used algorithms in all of data mining, probably. So let's just quickly review it. So we're going to, again, we're going to create this set of centers, and the size will be some parameter k. So we're going to choose a set C, where the size of C equals k. And so I'm not going to specify now how we do this. This could be arbitrarily. So then we're going to repeat in 2 steps. We're going to find all x, and so we're going to, let's say, create the cluster Si, which is going to be the x in the set x, where phi of c of x is equal to the center Ci. Okay, so we're basically just going to assign points based on this assignment-based function, right? So we're given the set of centers, and we do the assignment. Okay, so we could stop here, but we're going to repeat something. The thing is, this choice of these centers may not be the best choice, right? The solutions here from Gonzalez algorithm tend to pick them on the outside. Really, this center may be better kind of in the middle of the points it represents. So the next step we do is we're going to reset the center point. We're going to set Ci equals to the average of all the points in Si. So how do I take the average of the set of points? Right. So let's say that these points are the set Si. So the nice thing about the average is basically I take the average of every coordinate, right? So I look at the x coordinate, and I take the point which is the average. I look at the y coordinate, and I take the point which is the average, and then this becomes the new Ci, which is the average of Si. Okay? And so this is, but these 2 steps are inside the for loop, because when I choose a new center point, I'm going to actually, I may change how the points are assigned. I'm going to change the assignment function when I have a new set of center points. So I need to go back and reassign all the points. And so this is then going to choose a new set of assignment points, and then I need to go and recreate the average again. And so this is going to just keep repeating until some condition is met. Okay. So how you set this condition we'll kind of discuss. Okay, so now what might not be clear is why is, so the Gonzalez algorithm, hopefully this was clear why this was kind of minimizing, trying to minimize the case center. I'm always picking the point which is currently the point which is causing my case center maximum to be the largest, right? This is the argument, the point that has the maximum value here, and that's what I'm trying to minimize. I'm trying to minimize this quantity. For K-means, I'm trying to minimize the sum of the squared distances. For the K-median, I'm minimizing just the sum of the distances. Why is this, why did this associate with the K-means? So, well, okay, so let's look at the two steps here, right? There are these two different steps. So when I'm creating, in this first step here, in the first step, I'm assigning every point to the closest center. So I'm reassigning the points. And so it should be clear, in that case, it doesn't matter which of those measures I'm using, I'm always, this step is always decreasing the cost of any of those measures, decreasing it or keeping it the same. Right? By assigning a point to a closer center, that means that this sum, this element of this sum is going to decrease. Okay, so let me, right, so let's say we have some cost of x and c, and if I write this as x minus phi of c x. So if I assign x to a center which is closer, if I make the center that's the element of this assignment function closer to x, then this cost function has to decrease. Each of the terms in the sum is decreasing. Right? So this step must be decreasing this cost function. Okay, so what's interesting is that taking the average is also going to be decreasing this cost function. Okay, so I'm going to write this in a slightly different way. So I'm going to have sum over all of the different clusters. So all the points that are in cluster SI. And at this step, the assignment to the clusters is fixed, right? So I'm not changing how the assignment is to the clusters. And then here I can do this of x squared, but really inside of this sum here, this quantity is always going to be Ci, right? So everything in this sum is going to be mapped to the same center. Okay, and so my claim is that by taking this average, I want to say is this sum is decreasing. So I want to say is each of these terms is going to be decreasing. Okay, and so in fact, what happens is the average is the point which minimizes the sum of the squared distances to, if I map all the points to a single point, the average is the point that minimizes the sum of the squared distances. So this is a point of that's caused various confusion. I mentioned to you that at some point, I think in the 1950s, they tried to they were trying to come up with the so what was there? They claimed they wanted to find the point in the U.S. that minimized the sum of the distances to the entire population. And they did it by computing the average. And it was the wrong point. It minimized the sum of the squared distances, which was a different place in the U.S. So someone went and put a flag down, and it was not measuring what they thought it was because this confusion. This minimizes, finding the average here is what minimizes CI. Right, so there's this property that the average of SI is equal to the arg min CI in RD of this sum over x and si of the distances from ci to x squared. Right, so I minimize this quantity when I choose the average. So then if you combine these two steps together, what's happening is that every time I do either one of these steps, this total quantity, this total cost function is never increasing. It might stay the same if I don't change anything, but it can't increase. Every reassignment of a point to a new center is decreasing that cost, and every time I take the average to assign a new center to the set of points, it's also decreasing that cost, or at least not increasing. It may stay the same. So this is trying to minimize this cost. Okay. So this is basically the algorithm, and this is why this is called the K-means, because you're finding points which are the means of these sets of points. Okay, but there are a couple of questions left about here we haven't answered. So you're going to go through this here, some R number of rounds, right? So you're going to repeat these two steps some R number of times. So when do we stop?
Convergence?
What?
When it converges?
When it converges, yeah. So is R or when to stop. So when it converges. So what do you mean by when it converges? What does that mean?
It's the same x and y value repeats, so that's called a convergence.
Yeah.
If it's more than 2 times, it's considered.
So one kind of classic way, this is what I was looking for, is that means that no center CI changes, right? So when I'm doing step 2 here, this is not changing. Okay, so the first question, is this ever going to stop? Maybe every time I run it, it changes a little bit. Is this ever going to reach a point where the centers don't change? Can we guarantee that?
No.
No. So who thinks the answer is going to stop, and who thinks it's going to? There are examples where it may keep going forever. So who thinks it's going to stop eventually? And who thinks it's going? There are examples where it keeps changing forever. Okay. So it turns out it is going to stop. Okay, so that's good. That means this is surprising. So it will eventually, it must eventually stop. And so there's a simple argument why. So now if you think of it like the center's changing, this is kind of this continuous value. But if you think of it as the set of clusters, there are actually only a finite number of clusters. Right? There are only so many distinct ways I can cluster the points. Okay, so and every time, and I can never get the same set twice. Or if I do, then the algorithm must stop, right? Because then the centers, if the sets don't change, the centers won't change. And I know I won't get back to it because the cost was always decreasing. Right? So if I could see the same set twice because I would have to go to another set that had a lower cost and then go back up, which would lead to a higher cost. So that can't happen.
But you're taking average, right?
Yeah, I'm taking the average, yeah.
And then how you're saying you're only going for the points which are there, which are available to you. If you're taking average, it might not be even a point which you have already.
Yeah, that's right. So this point may not be in my set.
Yes.
Oh, but that's okay. Because the set of possible ways I can partition the points is bounded. It depends, it's a number that depends on n and k. Yeah, so the number of clusters, so the number of clusterings of size k is going to be n, what is it? So it's some combinatorial number. I forget, what is it? Yeah, so it's going to be k to the n, at most k to the n. Okay, so that means there are n points, and individually each can be assigned k different things. Right? So I'm going to have, that means if I look at point x1, x2, x3, up to xn, this one can be, its options are, it can be assigned to center 1, C2, up to CK. So I have k choices here. This one has k choices. This one has k choices. And so it turns out, in general, I can have k times k times k times k. That's k to the n different possible choices. So there's a bounded number. Okay, now this number is ridiculously huge. So so there are cases where it takes a really long time to run. And it's possible, actually, there are weird examples of K-means where the number of clusterings it goes through, the number of steps, is actually going to be exponential in n. And people have actually gone and created these examples and showed how to scale them to arbitrary sizes. There's really strange line of research. But there are these really bad examples. So, but it is bounded. So even though, you know, everyone thought it wouldn't converge well in practice, it could kind of keep going if you had a really weird example.
I think the cost function you said is non-increasing, not decreasing.
Yeah, so
how do you know there is no loop?
that's a good point, right? So what you're asking is that why couldn't you make a center, have two possible centers? So let's say I have this picture here. Where, and I'm not